Hey everyone and welcome to PrepFusion. I'm Anish and today we'll be starting the lecture 2 of time domain analysis, right? So in this lecture we'll study the ramp and parabolic response of first order systems. Then we'll do few more other first order systems where there are few more parameters which are involved, right? So in the previous lecture what we studied, we first got a brief overview of the time domain analysis chapter. Then we did was the unit step and the unit impulse response of the first order systems, okay, and also we learned a bit about steady state error for a unity feedback, okay. For more knowledge about the steady state error, we learn that in the next few lectures, right? So now let's first do this one. First do the ramp response of a first order system, right? So if I want to do a ramp response, what will be my Laplace transform from input? Laplace transform of input will be basically R of s equals to 1 by s square, okay. This is my Laplace transform, and like the response, what we call the response as, if we have given the input as ramp, then what is the response? Response is called like ramp response, okay. Response is known as ramp response, right? So this is known as a ramp response. Now we know the transfer function, it doesn't change, right? Transfer function remains same, okay, irrespective of the input or output. So what is the transfer function? C of s upon R of s equals to simply 1 by 1 plus s tau, right? This was the basic first order system. So now I will simply replace R of s with 1 by s square. So I went directly from here to here. I hope you understand, right? The Laplace transform of ramp signal is 1 by s square, right? So yeah, revise the first chapter, okay. So now what I will do, I will simply put C of s and multiply 1 by s square on that side, on the right hand side. So this becomes like, I will convert this into standard format. So I will take the tau common from s, so s plus 1 by tau and 1 by tau, and this is 1 by s, right? So yeah, this is my output basically. Now what I will do, I will simply, this is 1 by s square, so again I have to do partial fraction. So this time I will write like C of s in terms of this one. So okay, this will be a by s square plus b by s plus simply 1 by, okay, I will write this as c by s plus 1 by tau, and on the left hand side what do I have? I have simply 1 by tau into s square into s plus 1 by tau, okay. So yeah, this is basically my like the left hand side and right hand side. I've just broken down into like different terms of the denominator. Now I will use that formula, right, for partial fraction. Basically I will equate the coefficient also, and I'll put s equals to minus 2, s equals to minus tau also. All those things I will do. So basically, right, if I multiply both sides by this s square into s plus 1 by 2, what do I get? So 1 by tau equals to a into s plus 1 by 2 plus b s plus 1 by 2 plus c s square. So I hope you understand. I'm multiplying s square into s plus 1 by 2, right? So yeah, this is what I get. Now I will just put s equals to minus 1 by tau, okay. Then this will be gone, this will be gone, only this will be remained, right? So this is c into minus, like at, let me write this in different color, s equals to minus 1 by tau whole square equals to 1 by tau itself, right? So my c, right, c is tau only, okay. So now I will put s equals to 0. If I put s equals to 0, what do I get? putting s equals to 0, I get this is 1 by tau, this is gone and this is also gone, right? Only this is remained, so this is a times 1 by tau, so my a equals to 1. Now what I'll do, I will equate the coefficients. I need b, right? And b is always with s, so bs times 1 by tau, and here do I have any other s terms? I don't have any other s terms, right? So am I making any mistake? This is s, yeah, I have another s term, I forgot. This is a into s, right? So yeah, like equating the coefficient of s, right? So let me do it in the next page. Equating the coefficient of s. Okay, so if I equate the coefficient of s, what do I get? So this is a times s, so this is like a plus, and this is bs times 1 by tau, so this is also b times 1 by tau, so plus b by tau should be equal to 0, because at the left hand at the left hand side I don't have any s term, right? I have s to the power 0, but s to the power 1 has coefficient of 0, so here also it should be 0, right? That's why my b becomes minus tau of a. And what is a? A is 1 only, right? A is 1, so my b becomes minus tau. So what does my c of s, that is the Laplace transform of output, become? So my Laplace transform of output, c of s, is simply equals to 1 by a square, because a is 1, b by s. B is what is b? B is basically minus tau, right? So b by s, okay, plus tau, because c is tau by s plus 1 by tau. So s plus 1 by tau. So this is c of s. Okay, so now what I'll do to find the output response, right? Basically the ramp response, I'll take the inverse Laplace. So if I take the inverse Laplace, okay, where did it go? Okay, yeah, to take the inverse Laplace, I will take the inverse Laplace. So inverse Laplace of, what is inverse Laplace of 1 by square? We just did, right? What was it? It was t, right? T ut. Ut I will take in common, okay, with all of this. So it was t. Now what is Laplace inverse of 1 over s? It is ut only, and I have minus tau also, so this will be minus tau into ut. And what is the Laplace inverse of 1 by s plus a? It is e raised to power minus at, right? So it is e raised to power minus t upon tau. Okay, a is 1 by tau. So this is e of t. Okay, so this is my c of t. Okay, so this is my basically ramp response, right? This is my ramp response. Now what I have to find here, sorry, I forgot one thing, there was also tau here, right? Like this one, this tau I forgot, right? So this is my tau. Now this is my ramp response. Okay, now I will write this as ramp response. Take some other ramp response. Now I have to find the error, right? What was error? Error was simply, for a unity feedback system, it was r of t minus c of t. I will find using the both methods. So first method was like the basically the steady state error. What was the first method? First method was like this e of t, right? E of t equals to r of t minus c of t. Okay, so this is my e of t is equals to. So what is my r of t? R of t is ramp itself, so it is t minus c of t. Now c, like I will take e of t at the common outside, so this is minus of t minus tau plus tau e raised to power minus t upon tau, and whole is ut, right? This is my error signal basically. Okay, but I have to find the steady state, right? So e of infinity, what will it will be? So this t and this t gets cancelled. So first of all, let me cancel these two. I will be remained with this tau minus tau e raised to power minus t upon tau, okay, and 3 of t. Okay, so this e of infinity. What is e of infinity? E of infinity is basically this will decay down, right? This is the like decaying exponential. This will decay down. We have only tau left, so this will be only tau. Okay, so I will be remained with only tau, right? So my steady state error in this case, right? So steady state error in this case is tau. Okay, for a unity feedback system there will be always an error of tau. Why also I will explain. Okay, but let's find it in the some other way. So like with the help of Laplace, right? So if I want to find with the help of Laplace, so what was ESS equals to? This is basically my ESS. So my ESS, right, it was equals to limit s tending to 0 s r of s 1 minus t of s, right? Okay, but for this system is stable, so yeah, like the poles needs to be on the right hand side. Let's see if they are. Okay, so obviously we've got a finite answer from the previous method, so obviously they are, right? So limit s tending to 0 s times 1 over s square, because this is a ramp input, right? And what is the transformation? It is still the same, which is 1 by 1 plus s tau. Okay, so limit s tending to 0, we have 1 by s, and this is like 1 plus s tau minus 1 divided by 1 plus s tau. Okay, so what do we get? We get limit s tending to 0. So this is basically 1 cancels out, so we're only left with s tau on the numerator. So s tau on the numerator, and this is 1 plus s tau divided by 1 by s. Okay, so this is cancels out, so now I can put s equal to 0. So if I put s equal to 0, this is tau upon 1 plus 0, so I get tau. So my so my steady state error, right? Steady state error is equals to tau only. Okay, so for a ramp response, the steady state is tau only. Why? Let's plot the graph, right? So if I plot the graph, this is my r of t. Okay, and this is my like c of t, right? So what is my r of t? R of t is straight line. Okay, ramp basically slope 1, right? So this is time axis, right? So this is my r of t. Now what is my c of t? C of t is this, right? C of t is like this one is c of t, or like here this one is c of t, right? So it is a ramp. It is a ramp also, but it has some exponential component also, but it has some constant component also. So like from where does this ramp start? So at t equals to 0, what is the value? T equals to 0. I put t equals 0. This is 0. This is 0. Okay, and this is also 0, right? Like okay, let me take this one. So at t equals to 0, okay, my c of 0 equals to basically 0 minus tau plus tau into 1, right? E to the power 0 is 1 only, so it becomes 0 only. So there at the starting there is no error. Okay, but what happens, let's say if it is t equals to tau, what happens at t equals to tau? This is tau minus tau plus tau e raised to power minus 1. Okay, so this becomes like this, cancels out, and this is tau e raised to tau by e, right? Tau by e. But what is my value of t? Like what is my value of input at t equals to tau? But okay, let me do like this. Compare like the input and output both. Okay, r of 0 is simply 0, right? It is equal to t only, so r of t is t ut. Okay, Now what is my, okay, let me take this here and take this in the bottom. T equals to tau. Okay, r of tau equals to basically tau. It is equals to t only, so it is equals to tau only. Okay, so I see that this is tau and this is tau by e, right? So there is something less, lower than my input, so it will lie somewhere around here. It will go something like this and it will lie somewhere around here, and there is some transient, so there will be some transient, then it will die down and it will also increase linearly, but there will be always some constant error of tau. There will be always some constant error of tau. Okay, so that is basically the RAM response. Okay, because what I see at t equals to infinity, my like my this value, okay, at t equals to infinity, this value becomes t minus tau. Okay, t minus tau, this goes to 0. Okay, and my this value only is t, right? So there is some difference of tau every time. So initially it will be 0, some transient will come, then also it will go like straight line. Okay, like this, and there will be some error between these two. What do you say, like the error is like this one only. Okay, this one is the error actually. There it is, tau, right? There is tau. Okay, one time constant error is there. Okay, so that is the basically the difference between both of them, right? The sequence, this is r of t, this is r of t, and this is c of t. Okay, so yeah, now, right, this was a RAM response. Now let's solve for the parabolic response. So this is the parabolic response. Now I will not solve this using Laplace. Laplace is homework for you. Okay, so like this one, right, what we could have done is, like I solved here, right, using the Laplace, right? Using the Laplace I solved. What I could have done is, I forgot to do that, so I will do that here. So without Laplace, so this was the method 1. Okay, using transfer function, right, using Laplace basically. So what I can do is the other method basically. What is the RAM response? So RAM response, right, use some method 2. So RAM response, we know RAM response will be the simply integration of the step response, right? So it will go on like that only. Okay, because there is another 1 by system commit, right, and it is getting multiplied. So RAM response equals to basically integration of 0 to t of step response. Okay, with respect to, let's say, dt dash. Okay, it's just a dummy variable. So what is my step response? So my step response, if I go back, right, what was my step response? It was 1 minus e raised to power minus t upon tau. Okay, but where is it? Let's say, right, this one was my step response. So if I take it here, I need to simply integrate it dt dash, and this t is dummy variable, so this will also become t dash. Okay, this is just dummy variable, and this is also t dash. Okay, just to not get confused. And this is my RAM response basically. So this is my RAM response. So what I will get? I will get this one like this one. If I integrate this one, so this is t minus becomes plus, and also like 1 by 1 over tau plus e raised to power minus t upon, okay, not this is t dash actually, t dash upon tau. Okay, this is the integration basically of both of them, right? So we're moving from 0 to t. Okay, so let me use some different color. Actually, I'm searching for, yeah, so we'll replace with t dash with t and with 0. So this is t plus tau e raised to power minus t upon tau. Okay, also I will replace with 0 also. So this is replaced with t, and if I replace t dash with 0, this becomes 0 and this becomes 1. So we are left with tau, right? And of course don't forget the unit step, because like our system is like causal only, so we will start with after t equals 0. So yeah, this is the response that I get, right? So if I can see, like this is my c of t basically. So c of t here, what I get is c of t minus tau plus tau into e raised to power minus t upon tau, and here also I get the same, t minus tau plus tau into e raised to power minus t upon tau. Okay, so yeah, as you can see, like you can do this in seconds, okay, or you take much longer time with Laplace, right? So yeah, this is the basic thing that we can do, right? So yeah, now let's go for the parabolic response, in which I will not solve using Laplace. Obviously that will take me time. I will solve using this integration, right? So that Laplace is homework for you, so that will give you more practice on Laplace, right? So you should do the homework that I tell you, right? So yeah, I will just tell you the Laplace of this one. The Laplace of this one is 1 by s cube, right? One by s cube. So this response will be called as not ramp, sorry, parabolic response. Okay, so this response will be called as parabolic response. Now if I just solve it using that integration formula. So first one is, method one is using transfer function, Laplace transfer function. So this is basically c of s upon r of s equals to transfer function remains same, and my r of s equals to s cube, right? So basically, right, so like just put this here and solve. That is the homework for you. Solve. Okay, not here actually, put it here. So I will solve this using the method 2, that is the parabolic response like you might have a doubt, right, why we have it by 2 here. So the by 2 is nothing specific, it's just that to get this simple in terms of 1 by s cube, right? That's why simply getting it in terms of 1 by s cube, that's why I put a 2 here. Because if we directly take the Laplace of t square, it will not be just 1 by s cube, it will be 2 by s cube. That's why I multiply a half here to get rid of that 2, right? So why I want it in 1 by s cube? Because to do this, right, this one, yeah, this one, like the formula that I will apply, that parabolic response is equals to integration of 0 to of ramp response. To simply do that, and no other thing, constant multiplying, okay, that's why simply 1 by s is getting multiplied every time, right? Every time a 1 by s will get multiplied in time domain, it means we are doing integration. Okay, that's why I simply want it in terms of 1 by s. Okay, so yeah, now what is my ramp response? This is with respect to dt dash, obviously. What is my ramp response? Ramp response is this one, right? I will just simply copy and paste. My RAM response is this one. Okay, this is dt dash, so this is equals to, like if I integrate this one, this is now this will be replaced with t dash, and this is only 2, so t will be replaced with t dash, just a dummy variable. Okay, don't worry. So I hope you understand that integration. Okay, so if I integrate this one, what do I get? I get t square, t dash square by 2 plus tau, and what will happen is I will have 1 by tau, and this will be minus sign. Okay, just simply e raised to power minus at, if I integrate, it becomes 1 by a minus 1 by a, right? That's why. So simple integration only, minus t dash upon tau minus tau into t dash basically. Okay, constant integration, tau into t dash. So I will replace this with 0 to t. Okay, so what do I get? I simply get here is this will be t square by 2. Okay, this will be minus tau square into e raised to power minus t upon tau, and this will be minus tau t. Okay, so now, right, I have to put 0. This is t dash equals to t. Now if I put t dash equals to 0, so this is gone, right? This is also gone, only this is left. So I have again minus tau square. Okay, this is also 0, so this is 1 only, right? 1. So I am only remained with minus tau square, right? Minus tau square, and I am subtracting that. Okay, so minus into minus tau square. Okay, so what do I get? So let me rearrange the terms. This is t square by 2, and I will take common tau square, so this is tau t, and this is plus 1 minus e raised to power minus t upon tau into tau square. Into e of t. So don't forget e of t. This is a causal sequence, right? So yeah, this is what I get as my c of t, right? C of t. This is my parabolic response. Okay, so now what is the error this time? So error will be again for a unity feedback, right? It will be c of r of t minus c of t. So what is my r of t? R of t is basically this one. Okay, so I will copy this one. Sorry, not r of t, not this one. R of t is only t square by 2, right? T square by 2 minus this one, right? C of t. Okay, so basically if I subtract these two, what happens? Okay, I have to put this in bracket also. Okay, this is in bracket. Okay, yeah. Now, right, what will happen? This t square will get cancelled, but all this will get still be remain, right? So, and there is a like non decaying terms also, so we will get tau into t minus tau square. Okay, so what is basically, this is my error signal. So what is my steady state error? Okay, steady state error is basically e of infinity, which is basically unbounded, because this dies down to 0. We are left with tau square into infinity. So basically it is tau infinity minus tau square. So what do we get? We get infinity only, right? We get only infinity. So basically, right, this is unbounded. So obviously I will not use that Laplace formula, final value theorem, that I will not use. Unbounded, right? So for this my error is unbounded. Okay, so for this I will not find the error. Okay, so yeah, so let me we finished all the responses, impulse, step, ramp and parabolic. Okay, now I will just quickly summarize all this, right? Quickly summarize. So for impulse, so first one was impulse, right? When the input was impulse, what was my output? It was a decaying exponential, right? Decaying exponential. Okay, so simply it was something e raised to power minus t upon tau, and this just tells us about the transient, right? Transient part, right? So like here, right, we have two parts, right? For the unit step, as I can see, okay, if I can go back in here again, yeah, this part, right? One is the steady state part and one is the transient part. So this transient part has already been derived in the impulse response, right? Okay, this one was a steady state. A steady state I'm reaching there, but this one is the transient part. That's why I wrote in the first point, right, that impulse response tells us about the transient nature of the system. Okay, so yeah, that was the transient part. Okay, let me write here also, like this is C steady state and this is C transient. Okay, C transient. So yeah, now this is the transient part. Okay, now what is the error? Error is not defined for impulse response. Okay, we don't find error for impulse because the impulse is just given and taken out. Okay, so error is always with respect to reference signal. There is no reference signal present, so there is no error for impulse response, impulse signal basically. Now for unit step, if I give unit step, what do I get? Simply integrate this one, I get 1 minus e raised to power minus t upon tau, right? So this is the standard one. Okay, here I should put u of t also. Okay, so I put u of t here also. So now, right, now what is the error for this one? So error for this one is this transient term, right? So steady, this is u of t, and u of t minus this one, we are only left with this one. So it is e raised to power minus t upon tau into u of t. Okay, so now, right, what is my steady state error? Steady state error is 0 only because it is decaying, right? Decaying exponential, so t equals to infinity, steady state error becomes infinity. Now if my input is ramp, what do I get? Simply integrate this one. This will be something like t minus some exponential plus some exponential and some tau, right? So let me copy that. We just did this in this lecture. So this one, okay, here, this one is the ramp response, right? Let me copy this fully. So this one is the ramp response. Okay, then what is my error? So my error will be simply minus this one, so we are only left with this one, right? So this will be simply, okay, let me write this down here. Okay, tau minus tau e raised to power minus t upon tau. Okay, so yeah, this is basically my error. Okay, so now I put t equals to infinity for steady state error. So if I put t equals to infinity, I am only left with tau. So this is tau. Okay, so this is basically tau. Now right, if I the final parabolic, for parabolic I will not find the error because it is unbounded, we already saw it, right? What is the response? Response is here only, right? Simple, here only. Okay, this is the response. This is a brief overview of the table. Okay, so the like a brief summary basically. So yeah, summary I have already written. So this will, like, at once you will, at a glance you will see all the responses, right, at a glance. Okay, so yeah, this is that, this one, an error signal is like unbounded only, that doesn't matter anyways. Still I will put the error signal over here. Okay, and it is infinity. Error is not finite, right? Error is not finite. Okay, so now, right, now basically what we'll do, we'll study about few more first order systems, right? So there are few more first order systems that we need to study, which are dependent on different parameters basically. So yeah, let me do I have, yeah, first order system with non-unity DC gain. So like if the DC gain is non-unity, then what will happen? So what do you mean by this? So the let me write the governing equation, then let me do the Laplace transform, and from there you will understand. So if my first order system is defined like this one, right? Let me write the governing equation. So the governing equation, right, is simply this one, that my tau dash, like I have tau dy, not dy, let me, like as I my output is c, okay, I will write it in terms of c only, dc of dt plus c of t, right, equals to b r of t. So now, right now, my basically b should not be equals to 1, because if it is equals to 1, then it becomes unity gain, the same thing only. Okay, b is not equals to 1 and b is a real number, right? B is a real number. Okay, now, right, now can I convert this into Laplace? If I convert this into Laplace, then what will happen? Searching for other pens, yeah, this becomes tau into s into c of s plus c of s equals to b into r of s. So yeah, this becomes this one. Now I will find the ratio of c by r, right? So c of s equals to 1 plus s tau, right? 1 plus s tau. So this is b by 1 plus s tau. So this is my basically transformation. So what did I get? What is the DC gain? What is the DC gain? DC gain, like DC gain of CLTF basically equals to T of 0, which is equals to b by 1 plus 0, which is equals to b itself, right? Which is equals to b itself. So my DC gain is b, right? DC gain is b. So now, right, what do I say? B is not equals to 1, so this is non-unity, right? That's why the name is first order system with non-unity DC gain. So okay, so it is non-unity, so that is the reason we name it like this one. But everything else is same, right? As I can see, the time constant is same, the pole location is obviously the same if time constant is same, so the dynamic behavior will be same. Just instead, if I give a unit step, it will go to b, right? It will go to b, right, instead of 1 as steady state. So there will be b. So here, right, the error will be different. Okay, so here with respect to what you have to calculate the error, that we'll see okay later. So I will not draw the block diagram here. I will just find the response, step response, and yeah, that is just but for solving purpose for different systems, right? So what is the unit step response of this one? So error I will find in like other lectures. Okay, so what is the unit step response? So simply unit step response, I will not even find the impulse response. Just we'll check what is the difference in the first case when there is a unity DC gain and non-unity DC gain in this case. So for unit step response, my R of s equals to 1 over s, right? So what is my transformation? Transformation is this one, right? So okay, I didn't even put equals to here. So if I solve this, right, so my C of s, I will multiply 1 over s on that side, so this will become b, and also I will take the tau s common from s, so b upon tau into s into s plus 1 over tau, right? s plus 1 over tau. Okay, so what does this become? So basically, right, I have to do partial fractions. So if I do partial fraction, b over tau. So now if I put s equals to 0, so one thing you do is make this outside, right, so that you don't get confused. So this is 1, okay, and this b by tau, right, it's outside. Okay, so this, right, this becomes like if I put s equals to 0 here, this is 1 over tau, so this will go up. Okay, so this will be tau by s. Now if I put s equals to minus 1 over tau, again this minus tau will go up. Okay, and I will get minus tau by s plus 1 by tau. Okay, so basically, right, this tau will get cancelled. Okay, I will take tau common, this will get cancelled, and only b will remain. So c of t be b into 1 over s minus 1 over s plus tau. So is this like 1 over s plus 1 by tau? Is this something familiar from the first unit response from the first system? Okay, this is basically familiar, only a b term is multiplied, right? So as this is a linear system, right, only the gain, dc gain, will be multiplied, nothing else will change. All of the response dynamic behavior will be same, just the gain will be multiplied, right? So as this is a linear system, so c of okay, I wrote it c of t. Okay, I should have write it c of s. C of s, I will what I will do, I will do the Laplace inverse, right? Do the Laplace inverse. So if I do the Laplace inverse, what do I get? C of t equals to b into 1 minus e raised to power minus t upon tau. Okay, so this is e of t basically. This is e of t basically. Okay, so this is my p, right? This is my b. So okay, so this is what I get as my response, step response. So basically what is happening, this is simply getting scaled by b, as this is a LTI system. Okay, so yeah, now right now I will just draw the waveforms. Okay, draw the waveforms. My input is a unit step, right? So it is only one here. Okay, this is my r of t. Okay, let me color this actually. E of t, this I will color this. And what is my output? This is with respect to time. What is my output? Output is basically c of t. So my output is something like this, right? B can be more than 1, also less than 1 also, so it depends. So it can either go above the input or below the input. If B is less than 1, it is known as attenuation, and if B is more than 1, it is known as gain, right? So yeah, this is B. Okay, and like what is the response? Simply scaled by B, right? So this is B into 1 minus e raised to power minus t upon tau. Okay, simply scaled by B. Okay, so yeah, this is my c of t. But as I can see, it doesn't necessarily mean if I give an input of 1, always I will get some steady state value of 1, right? If there is some DC gain, it will be B multiplied. So yeah, as this is a linear system, so if the DC gain is B, it will get simply multiplied, right? It simply gets scaled. So this is my c of t equals to okay. So yeah, and this is my input. So yeah, this is the basically response. So like this time what like from final value theorem also I can find the unit step response, right? Instead of using like doing the Laplace transform. Okay, from final value theorem also I can find the unit step response. What I will do, okay, using I mean not the unit step response, the final value of the unit step response. Okay, so the like c of infinity equals to limit s tending to 0 s c of s, right? So this is valid for a stable system, stable, and c of s is stable, right? The poles are lying in the left hand side. Okay, the poles are lying in the left hand side. So yeah, as this s is getting cancelled, so it is okay. Like sc of s should have poles lying on the left hand side, so yeah, that is fine. So this is simply 1 by limit s tending to 0 1 by s tau plus 1. Okay, and I have a b also at the above, right? B also is here, right? Okay, this is the tau also, this tau is there. Okay, this is the transform function, right? B upon 1 plus s tau. Okay, so I am writing this, I haven't take tau common. Okay, please don't get confused. If I take tau common, then this will be b by tau, but here also there will be 1 by tau, and the tau will get cancelled. Okay, just solve it for yourself, you will understand. So this becomes b only. Okay, I get b. So what does this mean? This means this is the, for a unit step response and for a LTI system, first order system, this is the steady state DC gain. Steady state DC gain. Why steady state DC gain? Because I'm giving it some DC signal of 1, right? Then it is scaling it by b. That's why at steady state I'm getting a gain of b, right? B by 1. That's why this is known as steady state DC gain. But this is only valid for the stable system and obviously for unit step response. Okay, so this is just a terminology. No need to remember all this, right? These are not important. Just for I have to say everything to you, right? Say all the informations. That's why I'm telling you this is the steady state DC gain. Okay, for unit step response and for a first order system. Okay, which is stable basically. So now we'll understand the third form of first order system with non-unity DC gain, and also there is also a time delay, right? There is also a time delay here, right? So all these are, right, practical systems that are used in industry, right? That are actually used in industry. So we have non-unity DC gain, that is fine. That will be B into U of t. But what else will be there? The input that I'm giving will also be delayed by TD, right? So if there is some delay, the input is also delayed, right? So what is the governing equation? Governing equation is basically this one, right? So everything else is same. My time constant is same, dc of dt plus c of t equals to b. This time instead of simply r of t, like dc gain is there, right? Instead of simply r of t, I have r of t minus td, a time delay, right? Let me write this as capital TD. R of t minus td. Okay, so like previous case, I forgot to tell you that this is a 2-parameter model. Why? Because I have a tau, time constant, which can also vary, and this b can also vary. So this is a 2-parameter model. So this is b and tau, b and tau, right? So this is a 2-parameter model. So now, right now, yeah, this is a 3-parameter model. Why? Because there is a TD also, right? 3-parameter model, and the first one was 1-parameter model. So like tau, b and TD. Okay, so yeah, this is 1-parameter model. Now what I'll do, I'll simply take the Laplace inverse, right? If I take the Laplace inverse, what do I get? So this is tau s into c of s plus c of s equals to b r of, like, what is the Laplace inverse of a delayed signal? It is that signal multiplied by the exponential into e raised to power minus std. Okay, again first chapter, right? First chapter revision, very important. Okay, so like first chapter has been a while, actually it has been a while, so you have to revise. Okay, so this is b r of s into e raised to power minus std. So my C of s will be equals to simply 1 plus s tau, and it is equals to b, let me write this like this, r of s into e raised to power minus s td. Okay, std. So now, right, what I will get? I will get C of s upon r of s equals to b into e raised to power minus std divided by 1 plus s tau. Okay, 1 plus s tau. So what do I see? I see the transfer function, this one. I know the output of this one, and something is multiplied with this one. So let's say, what is this? This is simply t of s multiplied with e raised to power minus td. So we just did the Laplace transform, right? Just did the Laplace transform. Okay. Now what I can do? Okay, I will not write it like this one. What I will do is, what is, I want to find the unit step response. Okay, but before that, first thing we have to notice that I will do the unit step response. But before that, what we have to notice is that this is a multi-dimensional problem, right? Multi-dimensional. Why? Because e raised to power minus std, I can break it down in terms of series, right? In terms of exponential series, like this 1 minus std minus std whole square by 2 factorial, then plus std whole cube by 3 factorial, like that. Okay, not minus, sorry, that was plus std square by 2 factorial, right? That power formula, right? Series formula. So this becomes a infinite dimension problem. Obviously we can't solve this, right? In control system we can't solve this. Okay, also, like, you see that we have more zeros than poles, so that is also a problem. For a proper transfer function, the number of zeros should be less than number of poles, right? For this exponential, right? Now what we do, we use the Parabolic approximation. Okay, I will not do the derivation here, I will just give you a bit of intuition. So Parabolic approximation we use to solve this type of questions, right? Okay, so what do you do? So what is my C of s upon r of s? So this Parabolic approximation, right, we do the first order Parabolic approximation. So this is the first order Parabolic approximation, right? So there are second order Parabolic approximation also, that we will not do. Okay, just simply, right, what we do is, I can write my e raised to power minus std, right, like this form, that numerator I have e raised to power std by 2. Okay, and in the denominator I have e raised to power plus std by 2. So if you again resolve this, right, you will get the same form back, right? You get the same form back. Okay, now, right, now what I do, I, like, one thing, you know, if I do the linear approximation of an exponential when this std is very small, right, very small, I can do the linear approximation. So like that you can understand the Parabolic approximation. There is some big proof that I will not go through right now. Okay, so basically, right, so if I do the linear approximation, this numerator becomes minus std by 2. Okay, and this denominator becomes 1 plus std by 2. So if I break it down into series, that series formula, right, e raised to power minus std, if I break it down, I only consider the up until the linear terms. So linear term is this one and this one. After this, it is getting squared, right? And if std is very small, so square of that will be even more smaller, so I can ignore that, right? So yeah, that's why. So I can explain you. So e raised to power minus std by 2 equals to 1 minus std by 2, then this becomes 1 plus std, because minus whole square becomes plus std by 2 divided by 2 factorial basically, and this goes on, right, this goes on. Now this one, right, this, as std by 2 is already small, this will be even more smaller. 0.5 whole square is 0.25, so that becomes more smaller. So I can ignore these terms if I assume my std to be small. Okay, if I assume my delay to be very small. Okay, so yeah, we assume that our delay to be very, very small, and we come to this conclusion, right? So now what does my transfer function become? So my transfer function C of s upon R of s becomes b into simply 1 minus bstd by 2, okay, divided by 1 plus s tau into 1 plus e raised to power plus std by 2, okay. So yeah, this is basically my transformation becomes, okay, sorry, this is not exponential, sorry, did I write exponential? Okay, no, sorry, this will be, make this one bigger, that's why we did the approximate, right, to remove the exponential, but I am drawing the exponential again. So yeah, std by 2, right? So now what can we see? What is the order of the system? Tell me, what is the order? Is it 1? No, right? We have reduced the number of zeros from the numerator, but my order right now becomes a second order. It was first order here, okay, first order, right? And this, right, this becomes second order, okay, like this becomes second order system, right? So we won't analyze it here, okay, analysis will be complex. We'll analyze second order systems in next lecture basically. So okay, so we won't do the Laplace transform, but still I can find the unit step response. How? So what do we know for unit step response? What is my R of s? Okay, like this will be second order system, so analysis will be done for second order systems in the next lecture. So what is my R of s for unit step? It is 1 over s, right? So what is my transfer function again? So I will write this only, okay, I take this one only. So what does my C of s become? C of s is simply s td by 1 plus s tau into R of s, like is equals to 1 by s, okay, equals to 1 by s. So like R of s equals to 1 by s. So what do I know? That C of s equals to b by s into 1 plus s tau into e raised to power minus s td. Now is this familiar to me? I think this is right, because this was the step response of the second first order system, like yeah, this one, right? This one, okay. So if I name this as c dash, okay, and c dash of t I know, right? C dash of t I know. So what I will do is I will write in the next page. So C of s equals to c dash of s into e raised to power minus std. So now, right, if I take the Laplace inverse of this one, we know that if a exponential is multiplied in Laplace domain, okay, then we can simply do the what do you say, time shift, right? Time delay. If a negative exponential is multiplied, then I can do time delay. If a positive exponential is multiplied, I will do the time advance, right? So if I take the this has already been taught, basics, okay, basics again. So what will my C of t? It will be minus t naught or plus t naught. It will be minus t naught, right? So it is minus t naught. C dash, sorry, it will be c dash or minus t naught. So what is my c dash of t? Basically my like c dash of s, let me write, this is b upon s into 1 plus s tau, okay, and my c dash of t is simply, like it is just scaled with b, right? Same as unit step response of the first example, first order system. So 1 minus e raised to power minus t upon tau into e of tau. So I will just put a delayed version of this one, right? So what was the response of this one? The response of this one look like this, right? Something like this, okay, something like this, right? Okay, but now it will just be delayed. It will start from here, td. It will look like this. The dynamic behavior will still remain same. So yeah, let me plot the waveforms. Let me take this one only, previous waveforms only. Okay, so it will be delayed by td, right? It will be delayed by td. So like what will be my c of t this time? So c of t will be, let me write this, like this is my c dash of t, okay, and this is my c of t. So my c of t, c dash of t minus td, okay. Everything else will be same, right? Just the dynamic behavior has changed a bit. So it becomes like, how, what can I write my c of t as? C of t, I'll write here like this will be b and this will be 1 minus e. My t will change to t minus td. Okay, I will replace everywhere t from t minus td, right? So this becomes t minus td by tau into e of t. Also this t also changed to t minus td. So this is starting from td, right? Okay, let me reduce the size so that I can increase this one. So yeah, this is what my response is. So can I find the final value of the unit step again, right? If I find the final value of the unit step, I will get the steady state again, which will be again b. Okay, so from Laplace I can use final value theorem. System is stable, so I can use final value theorem as pole is lying on the left hand side of the experiment. So c of, okay, c of infinity is simply s times c of s limit s tending to 0. Okay, so yeah, what is like c of s? C of s is this one, right? C of s is, where did it go? No, not this one, this one, right? And I multiply by s. Okay, I have to put s equals to 0. So this s gets cancelled, right? So then I can simply put s equals to 0. This becomes 1. E raised to power minus 0 is 1. This also becomes 1. So I'll get again b. Okay, and again, right, this is the, again, like the steady state gain dc gain basically. Steady state dc gain basically. So this is my basically output, right? So dc gain remains same, transient behavior also remains same, it's just it is getting delayed. Okay, so these are three types of first order systems. First one was the basic one, then I had 2 parameter variation, and then I had 3 parameter variation. So here 3 parameters can vary. So these are 3 practical systems, first order systems that we use, right? And I plotted the responses, okay, and also gave you a bit of like other things also, bidirectional approximation, all those things, okay, and like all these things we did. So like this one was before, like the ramp response and the parabolic response. Ramp response has some error, finite error, which is tau, right? Which is tau. So if I give some ramp input, okay, if my velocity is constantly increasing, so there will be always be some error of tau. So keep that in mind in a first order system, normal, okay, with 1 parameter variation. In a parabolic, if I give some parabolic input, so some acceleration, right, some acceleration, then error will be infinite. So if I keep on increasing my acceleration, so acceleration is keeping on increasing, so error, it will deviate, right? It will deviate, so it will go to infinity. Okay, error will be, deviation will be infinity. So yeah, like that also you can keep the analogy in your head, how to remember all these things. Steady state error, whenever you talk about the error, like in our case, right, in undergraduate level, we always talk about the steady state error. Okay, we're always interested in the steady state error. So yeah, that is it for this lecture. In the next lecture, we'll start the analysis of second order systems.